The Kuiper Belt is a donut-shaped region beyond the orbit of Neptune. It's the home of Pluto, most of the solar system's dwarf planets, and some comets. Objects within the Kuiper Belt are often called, appropriately, Kuiper Belt objects, or KBOs. However, they're also sometimes called trans-Neptunian objects, although this is more of a blanket term for anything beyond Neptune. The Kuiper Belt can be compared to the asteroid belt, although their shapes are a little different, with the asteroid belt being flatter. Alongside the theoretical Oort cloud, the heliosphere, and Jupiter's magnetosphere, the Kuiper Belt is one of the largest structures in the solar system. More than 2,000 KBOs have been discovered, and astronomers believe there could be hundreds of thousands of objects that are at least 60 miles wide or bigger. There could even be millions of objects total. These bodies contain materials like rock, water ice, ammonia, and methane. The Kuiper Belt is thought to be the source of most short-period comets, particularly those that orbit the Sun in less than 20 years. It's also the source of the icy Centaur objects, whose orbits lie in the region of the giant planets. The existence of the Kuiper Belt was assumed for decades before it was actually discovered. Let's start off the exploration of this region by taking a look at how it came to be recognized. The Kuiper Belt is named after the Dutch-American astronomer Gerard Kuiper. He published a paper in 1951 speculating about objects beyond Pluto's orbit. However, Kuiper's work didn't predict the populations of objects in the region, nor their close relationship with Neptune. His ideas were really just the most well-known among astronomers, so it became attributed to him. Kuiper proposed the existence of a disc-shaped region of icy objects beyond Neptune, and he believed that this region was where comets originated. But Kuiper was not the first to suggest this region's existence. He also didn't believe it existed in the way it does. He thought there was no longer a significant population of bodies out there. In 1930, Clyde Tombaugh discovered Pluto, making it the first inhabitant of the region to be discovered. Though this was decades before astronomers knew about the region's existence, the discovery sparked speculation about the existence of other objects beyond Neptune's orbit. The same year Pluto was discovered, American astronomer Frederick C. Leonard proposed the existence of a band of small bodies extending from Neptune's orbit to a diameter of about 50 astronomical units. He based this hypothesis on models of the solar system's formation and the orbital dynamics of the outer planets. In 1943, Irish astronomer Kenneth Edgeworth published a paper arguing that the bodies of the solar system and their distribution were not bounded by Pluto's orbit. In other words, he believed there were more things out there. This can be seen as the genesis of the Kuiper Belt, which is why the region is sometimes called the Edgeworth Kuiper Belt. In 1951, Kuiper himself developed a stronger case. He demonstrated that a large residual amount of small icy bodies, specifically inactive comet nuclei, must lie beyond Neptune's orbit. A year earlier, in 1950, astronomer Jan Oort proposed the Oort cloud as the source of long-period comets. Kuiper thought of the belt region as the source of comets that the Oort cloud couldn't explain. Until direct detection, this became the best argument for the region's existence. In 1980, Uruguayan astronomer Julio Fernandez made a pivotal discovery that further reinforced the idea that short-period comets came from the edge of the solar system. His paper about a belt past Neptune is often credited as the first to correctly describe the Kuiper Belt. Later in the 1980s, Scott Tremaine worked with his colleagues to test the assertion that a belt past Neptune was the source of short-period comets. Their paper coined the term Kuiper Belt, and the name stuck, although Tremaine himself later admitted that it should have been named after Fernandez instead. Throughout the 1960s, 70s, and 80s, searches for anything past Neptune or Pluto yielded nothing. In 1983, the Pioneer 10 spacecraft visited the region, but because astronomers didn't know of anything out there, it just visited nothing. It passed through as a silent guest. Then, in 1992, David Jewett and Jane Liu discovered asteroid 15760, which at the time was designated 1992 QB1. This was the first trans-Neptunian object discovered, technically the second after Pluto, and it sparked discoveries of even more objects in the Kuiper Belt. The objects were so difficult to find for so long because they're very far away, very small, and very dark. The discoveries of these other objects, in particular one called Eris, called into question Pluto's designation as a planet. If Pluto was more similar to these other objects in the Kuiper Belt than it was to the planets in the solar system, was it really appropriate to keep calling it a planet? It was this question that led to clearer guidelines on what could be called a planet, and thus Pluto was reclassified to a dwarf planet. So far, one spacecraft has visited the Kuiper Belt with the goal of exploring objects within it. That spacecraft is New Horizons, which explored Pluto and Charon in 2015, and then Arrokoth in 2019. The Kuiper Belt is still a new frontier in space. We've only just begun exploring it, but it could hold vital clues about the solar system's history. Speaking of history, the Kuiper Belt is similar to the asteroid belt, not just in their shape and the objects they hold, but also in their origins. Like its friend in the inner solar system, the Kuiper Belt might hold millions of icy worlds that were left over from the solar system's formation. If not for Neptune, these objects might have come together to form a planet, similar to the asteroid belt's relationship with Jupiter. You may have heard of the Nice model. This is a scenario that could explain the origin of the Kuiper Belt. Per the Nice model, early in the solar system's history, Uranus and Neptune were forced to orbit further from the Sun because of shifts in the orbits of Jupiter and Saturn. While they moved outward, they passed through a dense disk of small, icy bodies that were left over after the giant planets formed. The gravity of Neptune, whose orbit was furthest out, bent the paths of these bodies inwards towards the larger planets. These bodies eventually encountered Jupiter, who slingshotted them into extremely distant orbits or just out of the solar system entirely. As Neptune tossed objects closer to the Sun, it caused its own orbit to drift further away. Its gravity forced the remaining objects into a range of locations where they can now be seen in the Kuiper Belt. The Nice model isn't perfect, of course, and it has its share of issues, but the fact remains that studying the Kuiper Belt can give us clues about where everything formed in the solar system and how it reorganized. And since we haven't figured out time travel yet, educated guesses are the best we've got when it comes to the solar system's history. The inner edges of the Kuiper Belt begin at around 30 astronomical units from the Sun, and the main region extends to about 50 astronomical units. This range spans from the outer edge of Neptune's orbit to where orbital resonances with the ice giant cause the number of objects to drop off. This also means it's up to 20 times as wide as the asteroid belt, and contains 20 to 100 times its mass. The outer edge of the Kuiper Belt is less clearly defined, but it generally excludes any objects that never come closer to the Sun than about 47.2 astronomical units. This distance is where objects in a 2-to-1 orbital resonance with Neptune are found. Overlapping the outer edge of the Kuiper Belt is a more disordered region called the scattered disk. The scattered disk continues out for about 1,000 astronomical units, but there are some objects on even more distant orbits. The scattered disk stretches far beyond the main part of the Kuiper Belt. It holds bodies known as scattered KBOs, which were thrown into highly elliptical and inclined orbits by Neptune. The orbits of many of these objects are still evolving, and some are lost over time. Some can travel hundreds of astronomical units from the Sun at their most distant, or closer to the Sun than Neptune at their closest. The scattered disk gives the Kuiper Belt a much wider and thicker extent. Some astronomers talk about the two as though they're different regions, although their boundaries overlapped and they're linked together. In particular, both regions probably resulted from Neptune's migration away from the Sun. The amount of material present in the Kuiper Belt today might be just a small fraction of its original size. According to the Nice model, as the orbits of the giant planets shifted, they could have caused most of the original material, which would have been about 7 to 10 times the mass of Earth, to be lost. Even today, the Kuiper Belt is slowly eroding itself. Objects within it collide and break apart to form smaller objects. These smaller objects continue to collide until they're nothing but dust, and that dust is swept out of the solar system by the solar wind. Today, the total mass of the objects in the Kuiper Belt is estimated to be no more than 10% of Earth's mass. The Kuiper Belt is the source of at least some comets that have been observed. Neptune's gravity can push objects towards the Sun, and then Jupiter further restricts them to orbits that last about 20 years or less. These are known as Jupiter family comets because their orbits are greatly influenced by the gravity of Jupiter. Because these comets have such short orbits, they make more frequent approaches to the Sun than others. This exhausts their volatile ices, and they eventually become dormant or dead comets with little to no detectable celestial activity. In fact, some near-Earth asteroids are actually dead comets that probably came from the Kuiper Belt. The Kuiper Belt isn't the source of all comets, though. Others, especially long-period comets with highly inclined orbits, are theorized to instead come from the Oort cloud, but that's a topic for another day. One of the early surprises when studying the Kuiper Belt was that its objects can be grouped by the shapes and sizes of their orbits. This let scientists understand several distinct groupings and populations of objects. The orbits of these objects provide clues about their history. KBOs are classified by their semi-major axis, their perihelion distance, and the inclination of their orbital plane with respect to the plane of the planets. Most KBOs are found in either the main part of the belt or in the scattered disk. There are also a couple of families that orbit the sun just inside or outside the main belt. These groups probably came from the Kuiper Belt originally, but were pulled out of the main region by the gravity of Neptune or another massive planet. First, there are classical Kuiper Belt objects. The word classical here means that these objects are on the type of orbit that Gerard Kuiper spoke about. Their orbits are the most similar to the original idea of what the Kuiper Belt was expected to be like. These objects are also sometimes called Cubewanos after the first discovered KBO, second after Pluto. Within the classical KBOs, there are two main groups, the cold classicals and the hot classicals. These terms don't describe the object's temperatures. Instead, they describe their orbits and how much influence Neptune has had on them. Both have a similar average distance of between 40 and 50 astronomical units from the sun. The cold classicals have orbits that are relatively circular and aren't tilted much from the ecliptic. They're mostly located in a band within 42 and 48 AU from the sun. They're often small, with none 500 miles wide or bigger. They're also redder in color than other KBOs, and they're likely made of the original material that composed the Kuiper Belt. Their circular and uninclined orbits mean that they haven't been disturbed much, if at all, by the other planets. Hot classicals, on the other hand, have orbits that are both elliptical and tilted. They're usually located at similar distances from the sun as the cold classicals, but their orbits can take them much further away from the sun. They're grayer in color than cold classicals, and they also tend to be larger. Most are found in a band around 12 AU thick, so they have a bigger range than the cold classicals. While cold classicals have orbits that never come close to Neptune, the hot classicals have had many interactions with the planet's gravity. Next are the resonant KBOs. These ones are simple. They're in orbital resonances with Neptune. Pluto, for example, is in a 2-3 resonance. It orbits twice for every 3 times Neptune orbits. There are enough objects in the same resonance that they even have their own name, the Plutinos. Detached objects have orbits that never bring them closer to the sun than 40 AU. Because these orbits don't come close to Neptune, it probably wasn't responsible for pulling them out of the Kuiper Belt. This means another force might be responsible. An undiscovered giant planet in a distant orbit, the gravity of passing stars, or gravitational perturbations that occurred as the Kuiper Belt was forming. Extreme trans-Neptunian objects are a very new grouping, and there are only a few members. They might eventually be revealed to not be part of the Kuiper Belt at all, as some of them can travel up to 1,000 AU from the sun. Centaurs are objects that travel through space between the orbits of Neptune and Jupiter. Because of this, they interact strongly with the gravity of the giant planets. These gravitational encounters mean the centaurs are unfortunately fated to either be ejected from the solar system or pushed further inwards where they become comets, or crash into the sun and the inner planets. The removal of centaurs is ongoing. It takes tens of millions of years for a typical object, and while that may seem long to us, it's actually quite short on a cosmic timescale. Centaurs are likely relatively recent escapees from the Kuiper Belt. Like the scattered disk objects, Neptune scattered them, but they just happened to go towards the sun rather than away from it. Pluto is the largest object in the Kuiper Belt, although Eris has slightly more mass. And even though Pluto crosses Neptune's orbit, it actually gets closer to Uranus than it ever does to Neptune. A fairly large number of KBOs either have moons or are binary objects. A binary is a pair of objects of similar size or mass that orbit a shared point in space between them. Some of these objects touch and create what's known as a contact binary. Binary KBOs are interesting because most of them are probably extremely ancient or primordial, and they haven't been altered much since they formed. They probably came to be through low-speed collisions, and these were more common billions of years ago, before Neptune disturbed the Kuiper Belt. Perhaps the most famous hypothesized resident that far out is Planet X, or Planet 9. Following Pluto's reclassification to a dwarf planet, some astronomers started to wonder if there could still be an undiscovered planet at the far reaches of the solar system. The main evidence for this planet's existence are the strange, elongated orbits of some smaller KBOs at the outskirts of the belt. These orbits could, in theory, be caused by the gravitational influence of an undiscovered massive planet. However, evidence beyond this is scarce and controversial. Planet X is by no means a certainty. It would be really cool if it's out there, though. And with that, we're done exploring the Kuiper Belt. I hope you enjoyed learning about this distant region of the solar system. I plan to make a couple videos talking about some objects in the Kuiper Belt, specifically dwarf planets and Arakoth, so keep an eye out for those. If you enjoyed this video, I would appreciate it if you could leave a like, and of course you can subscribe if you want to see more. That's all I've got to say for now, so have a good day, and I'll see you next time.